In today's lesson, I want to summarize a few of the ideas that have been in the background of a lot of these different example problems that you've seen with spectroscopy. And the first one refers to this concept of index of hydrogen deficiency, or IHD. The idea behind index of hydrogen deficiency is when you have a molecular formula of a compound, you actually have a good indication already regarding the sum of the different types of bonds that can exist in the compound. For example, in this compound right here, propane, when we look at the molecular formula of propane, there are 3 carbons and there would be 3, 6, 8 hydrogens. For a typical alkane, the number of carbons and hydrogens is related by the mathematical formula 2n plus 2. Meaning that if this n right here is the number of carbons. We can actually change this just to represent number of carbons. That tells you how many hydrogens that you have in a typical alkane. So if I have 3 carbons, then 2 times 3 is 6 plus 2 tells me that I should have 8 hydrogens. And this is an idea that cropped up way back when we introduced alkanes in the first place, and is simply the mathematical relationship between the number of carbons and hydrogens in a typical alkane. If we have 4 carbons, 1, 2, 3, 4, then this mathematical equation would tell us that we would expect 10 hydrogens. And there's 3 here, plus 3 more is 6, plus 2 is 10. So this mathematical relationship, again, tells us the number of hydrogens that should exist in a typical alkane. But we don't always have typical alkanes. And so there are 2 different types of bonds that can exist that cost you hydrogens. And the first one is a pi bond. If you put a pi bond between these 2 carbons right there, what ends up happening is both carbons have too many bonds. And so in order to fix the problem of the carbons having too many bonds, this pi bond requires you to remove 2 hydrogens. And so a pi bond creates what's referred to as a hydrogen deficiency. The same is true of a ring. If I try to connect the ends of this butane together to make cyclobutane, then again, both carbons have too many hydrogens, so making a ring inside of your system will also cost you 2 hydrogens. I'll clean this up just a tad. And so this index of hydrogen deficiency is essentially a numerical value that tells you how many pairs of hydrogens you've pulled out of the molecular formula in order to account for the various pi bonds or rings that are in the system. So index of hydrogen deficiency, or IHD, is also called SODAR. SODAR stands for the sum of double bonds and rings. And I don't like this SODAR. If I were to make up my own term, I would call it SOPAR, because it's actually the sum of pi bonds and rings. And I'll illustrate that with one more example. If instead of an alkene right here, I put in an alkyne, that tells this ChemDraw is telling me there's something wrong with my carbons, and it's because every pi bond that you add to the system requires you to remove 1 pair of hydrogens. So it's not just double bonds that create this index of hydrogen deficiency, it's pi bonds in general. This compound right here has 2 pi bonds, and therefore it is missing 2 pairs of hydrogens, or 4 total hydrogens. So the way that you determine the index of hydrogen deficiency, which is the term that I prefer to use because I don't like SODAR, and nobody knows what you're talking about if you say SOPAR, which would be technically more correct. So I'll just refer to it as IHD. The IHD is equal to the number of hydrogens that you expect to find in a molecule minus the number of hydrogens that you actually have in the molecule. And then we divide all of this by 2 because it's actually the number of hydrogen pairs that are missing, and that's the rationale for division by 2. Well, now we need to flesh out what is the number of hydrogens that I expect and what is the number of hydrogens that are actual. Well, the number of hydrogens that I expect is based on this chemical formula right here, this mathematical equation right here, that the number of hydrogens that you expect to find in a compound, I'll do this on a separate line So you can kind of see the process of thought here. So rather than type out number of hydrogens that we expect, we'll add in that formula. 2 times the number of carbons plus 2 is equal to the number of hydrogens that I would expect to see, minus the number of hydrogens actual, and for now, let's leave that alone, and apply this particular formula for the index of hydrogen deficiency to a variety of different problems. So let's consider first acetylene. Acetylene has the molecular formula of C2H2. And that name acetylene is one that I hope that you're familiar with. The chemical structure of acetylene would look like this, right? Whoops, there. This is acetylene. Now, because I've shown you the chemical structure, you should already be able to identify that it has 2 pi bonds. That 2 pi bonds is what the index of hydrogen deficiency would tell us. So our IHD is equal to 2 because I know what the structure is. But if we didn't know the structure and all we knew was that the molecular formula was C2H2, then we should be able to calculate the IHD by using this this mathematical formula down here, where it's equal to 2 times the number of carbons, and there are 2 carbons in acetylene, plus 2, and then we subtract from that the number of hydrogens that we see in this formula right here, so that's 2. And then we're going to take all of that and divide it by 2. So 2 times 2 is 4, plus 2 is 6, minus 2 is 4, divided by 2 is 2. So the math of C2H2 tells us that based on the number of hydrogens present in this molecular formula, we would expect the index of hydrogen deficiency to be 2, which tells us that there are 2 bonds that are either pi bonds or ring closing bonds. You can't have a ring between 2 carbons. That's just not enough carbons to have in a system. And so these are 2 pi bonds. Let's consider a rather tortured example of propylene, of cyclopropylene. Is it cyclopropylene? I don't know. Cyclopropene is for sure a name. Cyclopropylene, I don't know if that's correct or not. So anyway, if we look at the structure right here, you should notice that there are 3 total carbons in the compound. And therefore, the IHD calculation, IHD is equal to 2 times the number of carbons, and there are 3 carbons, plus 2. That's how many hydrogens we would expect to exist if you had 3 carbons. Then we're going to subtract from that the number of hydrogens that we actually observe. And there are 4 observable hydrogens in this compound. There's one coming off of this side over here. Whoops. And there's a hydrogen over here. And then this carbon right here has 2 hydrogens coming off of it. Hydrogen, hydrogen. And so because there are 4 hydrogens, then we subtract 4 from our calculation, minus 4. And then we take all of this and divide it by 2. So 2 times 3 is 6, plus 2 is 8, minus 4 is 4, divided by 2 is 2. And our index of hydrogen deficiency is 2. And if we see if that value right there matches up with our observable Lewis structure, 2 tells you that there are either 2 rings in the system or 2 pi bonds, or a combination of rings and pi bonds that adds up to 2. And that's what I'm seeing here. There's 1 pi bond and 1 ring. That's an index of hydrogen deficiency of 2. Let's look at a few more examples. So again, this is butane. Butane has 4 carbons in it. The number of hydrogens that we expect to see is 2 times 4 plus 2, and that's equal to 10, minus the number of hydrogens that we actually see, which is 10. And so the index of hydrogen deficiency would be 10 minus 10 divided by 2, or 0. And that makes sense. There's no pi bonds or rings anywhere in the system, so the index of hydrogen deficiency based on the Lewis structure is 0. Based on our calculation, it's 0. But what if we add a halogen to the compound? And so what we want to do is put a bromine anywhere in this compound that we want. And if you think about it mechanistically, if you want to add a bromine to an alkane, the first thing that you have to do is remove one of the hydrogens and then put a halogen on in its place. So it doesn't need to be bromine, it can be any halogen. And now if you look at the calculation, the number of expected hydrogens is strictly based on the number of carbons. I would still expect to see 10 hydrogens. 2 times 4 plus 2 is 10. But the number of actual hydrogens that I see is only 9. And so how do we account for this halogen right there? Well, this actually changes. So instead of subtracting the number of actual hydrogens, what we want to do is subtract the number of actual hydrogens plus any halogens that are there. So the number of actual hydrogens plus the number of halogens that are actual. And so mathematically with this one right here, if I run the index of hydrogen deficiency calculation, it's 2 times 4 plus 2, and that's equal to 10. And then the number of hydrogens that I actually have is 9 hydrogens plus the 1 halogen is equal to 10. 10 minus 10 is 0. Dividing it by 2 doesn't make any difference. And so the only thing, if we're trying to expand beyond just carbons and hydrogens and think about the full gamut of honk X options. If you add a halogen to the compound, then when you're doing your index of hydrogen deficiency calculation, you just treat the halogen like a hydrogen. The next question is, what happens if I put an oxygen in the system? Well, if you want to turn an alkane into an alcohol, if you want to add an oxygen to an alkane, oxygen requires you to make 2 bonds. So if I pluck this hydrogen off and then try to put an oxygen on in its place, that oxygen brings the hydrogen back with it. So what this tells us is that there is no need in anywhere in your index of hydrogen deficiency calculations to account for oxygen. So you don't have to incorporate oxygens anywhere in there. The number of oxygens in your compound does not have any effect on the index of hydrogen deficiency. The last example we want to think about is nitrogen. So if I take a hydrogen off and replace it with a nitrogen, notice how that nitrogen brings even an additional hydrogen with it. And so what happens with nitrogens is they actually affect this number of hydrogens expected. So if we update the full equation right here, then on the hydrogens expected side, we're going to add in any number of nitrogens that we have. So if you have a nitrogen in the compound, it ends up recruiting an additional hydrogen to the compound. And that's actually the basis of why nitrogens produce odd values for molar mass. So now we can come back and think about this equation one more time, the index of hydrogen deficiency, which is the same as the number of pi bonds or rings in your system, is equal to the hydrogens expected minus the hydrogens actual divided by 2, or multiplied by 1/2. Mathematically, that's the same thing. And then I went through and tried to explain how the number of hydrogens that you expect is 2 times the number of carbons plus 2 plus any nitrogens you have in your compound. That is how you figure out the mathematical value of the hydrogens that are expected. And the hydrogens actual are just hydrogens that you see in your formula plus any halogens that you see. So that's kind of a full introduction to this equation. What you really need to do right now is pause the video and try to calculate the index of hydrogen deficiency for each one of these 6 compounds, one of which we've already done, and then when you restart the video, you can check your answer against my answers. All right, so let's talk about these. In the first one, there is 1 carbon and a nitrogen. So the hydrogens that I expect to see would be 2 times that 1 carbon, which gives me 2, plus 2 gives me 4, plus a nitrogen gives me 5. The number of hydrogens I actually see in this first compound is 3. So it would be 5 minus 3 divided by 2, which tells me that the index of hydrogen deficiency would be 1. So only knowing the molecular formula, I know that that compound has a pi bond in it. It's not a ring in this case because there's just not enough atoms for it to be a ring. For the next example, if there are 6 carbons, then the number of expected hydrogens is 2 times 6 plus 2, or 14. There are 6 actual hydrogens, so 14 minus 6 divided by 2 gives me an index of hydrogen deficiency of 4. And pro tip, if your index of hydrogen deficiency is equal to 4 or larger, then you should start thinking there's probably a benzene ring in the system. For the next example, all I did was take the C6H6 and add an oxygen to it, and oxygen has no effect anywhere in this equation. So I'm going to see the exact same math. The number of hydrogens that I expect to see is 2 times the number of carbons plus 2. There are 6 actual hydrogens, so 14 minus 6 divided by 2 gives me an index of hydrogen deficiency of 4. So I would think there's probably a benzene ring in there. That would be my first assumption. C2H2, we did this one already. The number of hydrogens I would expect to see is 2 times the number of carbons plus 2. That gives me 6. There are 2 actual hydrogens, so 6 minus 2 divided by 2 is an index of hydrogen deficiency of 2. You can check that in your calculator if you need to. For the next example, there is only 1 carbon, so 2 times 1 plus 2 is 4. There are no hydrogens, but there are 2 halogens, so we treat that as if there are 2 hydrogens. 4 minus 2 divided by 2 gives me an index of hydrogen deficiency of 1. That molecule probably is phosgene. There's just not a lot of other ways to put carbon, oxygen, and 2 chlorines together. And if you don't know the structure of phosgene, then you can move on with your life or look it up. It's up to you. The last compound has all the atoms in it. So it's kind of a tour of all of the different rules. The number of hydrogens that I expect is 2 times the number of carbons plus 2. 2 times 2 plus 2 is 6. Plus there's a nitrogen in there, so I expect to see 7 total hydrogens. The actual number of hydrogens is 6 plus 1 halogen, which is also 7. And again, notice that the presence of the oxygen had no impact at all on the way that I did my math. This molecule has an index of hydrogen deficiency of 0, which tells me that knowing nothing more than the molecular formula, I can already rule out the possibility in this case, of there being any pi bonds or rings inside the system. I have promised to give you a Proton NMR memorization list for a while, so here it is. If a hydrogen is attached to an alkane, we typically see that hydrogen in the range of 0.9 to 1.8. If the hydrogen is connected to a vinylic group, in other words, if it is a simple pi bond and there's a hydrogen hanging off of it, then we expect that hydrogen to show up in the Proton NMR between 4.5 and 6.5, aromatic hydrogens between 6.5 and 8.5, aldehydes between 9 and 10, carboxylic acids between 10 and 13, and alcohols are nomads. They just wander and end up in all kinds of interesting places. Now, there is a problem with proton NMR spectroscopy, and that problem is the values are not that consistent. So this is pulled from a study that somebody did looking at the methyl group of toluene. So hopefully you're familiar with the structure of toluene. It's a benzene with a methyl group. There are 3 hydrogens on that methyl group, and we typically expect alkanes, which is what the methyl group of toluene is, to be in the region of 0.9 to 1.8. Now, toluene is a methyl group, but there's a benzene ring sitting next to it, so that's why it's a little bit outside of the high end of that range. And these are the shift values for the 3 hydrogens on the methyl group of toluene reported in 8 different peer-reviewed publications. And what you'll notice is there's quite a bit of variation. The average value is 2.24, the standard deviation of 0.11. And this is the same molecule being measured by multiple different NMR instruments. And so NMR is sensitive to temperature and concentration and has its own inherent error that occasionally occurs with any instrument. So this is why it's better to think about these things as ranges, plus or minus, 5 to 10%, rather than try to fixate on what is the exact value that I expect every time I see a particular functional group, because even if it's the exact same portion of that molecule, we see varying values from instrument to instrument. Vinylic hydrogens are hydrogens that occur just on the outside portion of an alkene. So here's my alkene. The hydrogen that is directly connected to it is a vinylic hydrogen. Vinylic hydrogens show up at shift values that are oddly high. So this is still a hydrocarbon, and even though it has a pi bond in it, you wouldn't expect for that pi bond to generate enough electron withdrawing, electronegativity type of interactions to push this compound all the way up to around 5. It's just kind of a radical shift of the NMR value that you wouldn't expect just based on the pi bond. Well, one of the things that happens with the pi bond is that the electrons in a pi bond actually go with the externally applied field. So remember, normally the bonds that we talked about in a sigma bond, if this is my externally applied magnet, the sigma bond will offset that externally applied magnet and shield the neighboring atoms from the full brunt force of that externally applied field. And that is true of sigma bonds. An alkene pi bond, on the other hand, reverses course and gangs up, adding to that externally applied magnetic field. And so these electrons in this pi bond are actually working against their neighboring atoms. So they are referred to as ring shielding electrons. Sorry, ring de-shielding electrons. So pi bonds do the opposite of what they're supposed to, and this is what gives pi bonds unusually high shift values in a proton NMR. If you have a conjugated ring system of pi bonds, then they actually produce what's called a ring current that significantly adds to the shift values. And benzene, which again is just kind of a normal hydrocarbon, it shows up much, much higher than alkanes do, and even higher than a typical alkene, because the pi bonds in the benzene ring are working with that externally applied magnetic field. A carbonyl group itself does not contain hydrogens. Carbonyl refers to the carbon and the oxygen that is double bound to that carbon. But there are two types of carbonyl groups that have hydrogens that are very close to the carbonyl group. The first type is an aldehyde. An aldehyde is when you have a carbon-oxygen double bond, that's the carbonyl, and there is a hydrogen that is directly connected to that carbon. This aldehyde uniquely shows up in the proton NMR spectrum between 9 and 10. There's really nothing else that shows up in that region, so it is a dead giveaway for an aldehyde if you see a peak between 9 and 10 in the proton NMR spectrum. The only thing in a proton NMR that will consistently show up at higher than the value associated with an aldehyde is a carboxylic acid. The hydrogen associated with the carboxylic acid has lost so much electron density and then has to deal with this treachery of the pi system, adding to that externally applied magnetic field, that it shows up with values between about 11, and I've seen them as high as 14, although that's very rare. 12 is definitely more standard. Notice that the hydrogens that are not directly connected to the carbonyl group, over here on this methyl group on the side, now fall back down to the typical range where we generally see alkanes. A little higher, alkanes are usually between 0.9 and 0.9 and 1.8 on this slide right here, but the presence of the carbonyl group causes them to go up a little bit. If they are directly connected to something in the carbonyl group, like an aldehyde, they'll go way up, and the carboxylic acid is also a very high value. So these two, aldehydes and carboxylic acids, are generally the highest valued peaks you see in your proton NMR. NMR gives us 4 different bits of information. It tells us the number of unique types of hydrogens. It tells us their approximate shift values. It also tells us about integration and peak splitting. If we look at this compound right here, there are 3 different types of hydrogens because there are 3 peaks. There is a hydrogen that is connected to this carbon that's directly underneath the oxygen. There is a hydrogen that is connected to this, there are 3 hydrogens connected to the methyl group, and there are these 2 hydrogens that are both vinylic. Vinylic hydrogens typically show up in the ballpark of 4.5 to 6.5. The 2 hydrogens here are equivalent to each other, so they produce a single peak, and they're just higher than the typical range of 6.5. There's a variety of reasons for that. The presence of the chlorines is certainly not helping, and the fact that this is a partially conjugated system tends to creep these values up into that territory where we normally see aromatic ring systems. This is not aromatic, but these hydrogens look a little bit close to the aromatic ring system because there is some conjugation in these in the carbons right here. Of the 2 remaining peaks right here, you would expect the methine carbon to have a higher shift value of its associated hydrogen than the methyl hydrogen would over here. So that's just methyl versus methine. Both of these are much higher than you typically expect to see for simple alkanes, and that's because they're not simple alkanes. They are connected to an oxygen, and they're next to this pi system. So these are pretty high shift values right here. You should also notice that everything is a singlet. and that's because the distance between any of these three groups of hydrogens means that all of the hydrogens are more than 3 bonds away from the next hydrogens, with the exception of the hydrogens down here on the bottom of the alkene. This hydrogen hanging off of this carbon is actually 3 bonds away from this hydrogen, but because those two hydrogens are equivalent, they don't actually split each other. So equivalent hydrogens will still produce a singlet even if they happen to be 3 bonds away from each other. Of the other things that Proton NMR can give us, integration is one of the most important. So here is a spectrum of C5H10O. And what you're looking at here, there are actually only 2 real peaks associated with this compound. And what they've done is they've taken this peak at about 2.5, actually it's at 2.42 because there's the number right there, and they have magnified it to allow you to look at it more closely here off to the side. So this particular spectrum does not have 4 peaks. It actually only has 2, and then these are magnified close-ups of those 2 peaks, and that should be obvious because the numbers right here are labeled and they try to change the background to help you out there. You'll also see a peak at 0. Remember that's the TMS that they add the tetramethylsilane as a standard. And then there's a peak right here right around 7.3, and that's the solvent that we use when we're conducting the NMR experiment. I told you before about how you have a line that traces the sum of integration values, and if you draw a double-headed arrow that extends from the bottom of where the line flattens out when you start to where the line flattens out when you end, and then measure that in some linear unit like millimeters right here, then you should be able to look at this numerical value, 33, compare it with the other numerical value, and approximate the whole numbers that this rounds to. So if you divide both of these by 16, 48 divided by 16 is 3, and 33 divided by 16 is really close to 2. So what that tells us is that for every 2 hydrogens that made up this peak, there were 3 hydrogens that made up that peak. In addition to integration and shift values and number of unique hydrogens, we also deal with splitting. So this is ethyl chloride. We've actually looked at this example before. The 2 hydrogens that are on this methylene carbon are the most d-shielded because they're closest to chlorine. So we see them on the leftmost position of our NMR spectrum. The methyl group is more shielded, so it's closer to the TMS peak. These 3 hydrogens, 1, 2, 3, are all equivalent, so all 3 of those go into making up this peak, and they are 3 bonds away from 2 hydrogens. So you can count if you like. From this hydrogen to these hydrogens over here is 1, 2, 3 bonds. And when I do that, I should prove to myself that these 3 hydrogens have 2 neighboring hydrogens that are splitting them. And if you split something twice, it ends up as a triplet. Whereas the 2 hydrogens at 3.42, they have 3 hydrogens that are splitting them. If you split something 3 times, then it ends up forming a quartet. So this is an example of splitting. And now in this lecture, you've again seen all 4 things that NMR spectroscopy can give us: number of unique atoms, approximate shift values of those atoms, integration, and splitting. We saw an example that illustrated this just a second ago when I pointed out that there was an example, this one right here, where the hydrogens on the bottom were actually 3 bonds away from each other, but it still shows up as a singlet, and that's this equivalency exception. So notice that ethane has 6 total hydrogens right here, and the 3 hydrogens on the right methyl group are 3 bonds away from the 3 hydrogens on the left methyl group. And even though both groups of hydrogens are 3 bonds away from each other, it still shows up as a singlet. And this is because hydrogens that are 3 bonds away will split each other unless they are equivalent to each other. So this is a case where that 3 bond rule doesn't apply when hydrogens are equivalent. Now let's answer the question, why? Why do hydrogens that are 3 bonds away cause splitting? And this is because of something that's called coupling. So consider the red hydrogens down here. In a proton NMR experiment, these red hydrogens would produce a peak at approximately 2.1. The blue hydrogen is 3 bonds away from all of the red hydrogens. And so we expect the red hydrogen peak to split. The reason that splitting occurs is because when these red hydrogens are absorbing a photon, they are fighting against that externally applied magnetic field. This blue hydrogen is randomly oriented because it's also catching photons, so that its nucleus is either lined up with that externally applied magnetic field or against the externally applied magnetic field. And what we find in an NMR experiment is that because of the way the photons are crashed into these molecules, the blue hydrogen is 50% of the time it's going to be in its magnetic field will line up with the externally applied magnetic field, and 50% of the time it lines up against it. And so when it lines up with the externally applied magnetic field, because it's a little bar magnet that is close to the red hydrogens, that means the red hydrogens no longer feel just that externally applied magnetic field. They're also feeling a slight bump in power of that externally applied magnetic field because the blue one is lined up with it and adding to the field strength. And so the photon that is required to flip the red hydrogens is going to be a little bit higher in energy because now you're flipping against the externally applied magnetic field and this neighboring hydrogen. So that causes the peak to move a little bit to the left-hand side. But 50% of the time, this blue hydrogen will be lined up against the externally applied magnetic field. That provides a very small shielding effect. So 50% of the time, these red hydrogens are actually, they don't have to use as much energy to flip, and that causes the shift value to drop down a little bit. So the splitting occurs because the neighboring hydrogen, if it's 3 bonds away, will act as a little bar magnet and either help, which shifts to the left, the externally applied field, or shield or hurt the externally applied magnetic field by shifting to the right. So that's the nature of what causes splitting. It's because those neighboring hydrogens are messing with that externally applied field. And the more neighboring hydrogens you have, kind of the more messing with that will occur in that process. This now leads us to the problem that we experience when we have diastereotopic hydrogens. So this particular compound right here has a number of hydrogens that are on the ring system. We don't care about them right now. What instead we care about is the nature of this hydrogen right here. If we look, there are 2 hydrogens that are 3 bonds away. So this color to me looks red, maybe pinkish. Relative, we'll call it pink, relative to the pink hydrogen right there, 3 bonds away is the blue hydrogen, and we'll call that green. And if those colors are not what you're seeing, then oh well. So the red hydrogen is 3 bonds away from both the blue hydrogen and the green hydrogen. When you have, and these 2 right here are diastereotopic, meaning that this blue hydrogen is, if we pulled this off and put a chlorine on in its place, that chlorine would be trans relative to the benzene ring. If instead you put the chlorine on this side, it would be cis relative to the benzene ring. So replacing the hydrogen with the chlorine generates 2 different diastereomers, and that tells us that these 2 hydrogens are not NMR equivalent. Not only will that cause them to produce unique and separate peaks, it also changes the nature of the way that they split their neighbors. So what you'll notice about this peak structure right here is how unsymmetrical it is. Asymmetrical is the word that I should use. Now I left this slide inside of the PowerPoint, and you could read it if you want. But I'm not going to try to explain it for the interests of time and everything else you've got going on right now. What I do want you to appreciate about that blue peak cluster right there is the symmetry associated with a quartet. And we've seen this before. If you have a quartet, it's short, tall, tall, short, and it goes up and then comes back down again. When you have a triplet like this, it has some symmetry. It starts small, the middle point is the largest, and then it gets smaller again. And so that symmetry of quartets and triplets and even doublets right here have that symmetry that they're both approximately the same height. When you have this type of asymmetric splitting because a hydrogen in question is adjacent to two diastereotopic hydrogens, what ends up happening is instead of getting a nice rounded out triplet, because two hydrogens should split twice and you end up with a triplet, you end up with what's referred to as a complex splitting pattern. And it's a splitting pattern that doesn't follow the simple rules that we've looked at so far. And the way you identify a complex splitting pattern is when it lacks the symmetry right there. So this is not a quartet. It's actually what's referred to as a doublet of doublets. It's a pair of doublets. And that, when you see this asymmetric, that instead of going some short, tall, tall, short, it just kind of does whatever it wants. This tells you that you've got some diastereotopic hydrogens inside of your compound, and you need to step away from trying to interpret the splitting pattern. It's essentially at that point just a mess. And we're not going to walk through the details of interpreting these complex splitting patterns that occur with diastereotopic hydrogens. Here's another example of this complex splitting pattern. Notice here that hydrogen B is adjacent 3 bonds away from hydrogen A and hydrogen C. And if you are 3 bonds away from 2 hydrogens, you generally expect to be a triplet. But if we look at the spectral data, here is the kind of the bird's eye view of the spectral data, and then this is the zoomed in view. This peak that corresponds to hydrogen B ends up making what looks like a quartet. And A and C have their own problems. What I want you to appreciate about B is that it's not a symmetric quartet. And so you need to step away and not try to interpret the details of the splitting pattern. You got to know when to fold them on this case, to quote the late great Kenny Rogers. Another example of a time when you should know when to fold them are the hydrogens associated with the benzene ring. Benzene rings have aromatic stabilization. This benzene ring right over here has 1, 2, 3, 4, 5 hydrogens. The problem with the benzene ring is that it is stabilized by aromaticity, and the molecule actually tightens up, shrinks down. And in doing so, it causes what's referred to as cross-ring coupling. So the hydrogen coming off of this carbon will not only split because of the hydrogen that's 3 bonds away from it, the ring shrinks small enough such that hydrogens on the opposite side of the ring actually are close enough that the magnetic field associated with this hydrogen will start to influence the magnetic field associated with the hydrogens across the ring system. And so this is just a case when you see peaks that occur between 6.5 and 8.5, you just need to realize those are aromatic hydrogens and their splitting patterns don't always make sense. There are 3 different types of hydrogens clearly shown. So these 2 hydrogens that are ortho are the same, the meta hydrogens are the same, and the para hydrogens are the same. But I'm not seeing 3 distinct peaks. Instead, what I'm seeing is one big messy lump. And that's because there's so much splitting going on that those splitting patterns just kind of overlap with each other and produce a smudge. This is the example I think I tried to give you earlier, where imagine holding your hand out in front of you so that it casts a shadow on the wall, and you can see in that shadow the outline of your individual fingers. Now take your other hand and just kind of sit it next, kind of behind the first hand, and the shadows should start to get blurry. And that's because you have overlapping shadow patterns that are falling on the wall now from your 2 hands. And this is what happens with hydrogens inside of a benzene ring, is that the splitting patterns start to overlap, and it just generally produces a mess. So instead of wasting our time with peak clusters that we can't really interpret, let's now focus on the blue and the red. We should be able to interpret these. The hydrogen attached directly to the oxygen is an alcohol hydrogen, and they tend to wander all across the spectrum. And so the fact that in this case it shows up at about 2.6, that's a little lower than I would have expected it, but alcohols wander. The carbon with the 2 hydrogens, and their peak is shown in blue, is a little higher than you expect for a typical methylene carbon. Normally they'll show up between 1 and 2, 0.9 and 1.8. But the presence of the benzene ring and the neighboring oxygen are definitely going to push those peaks to a higher value. What I really want you to notice about this is the fact that both the blue and the red are singlets. And if you think about the structure of that compound, that oxygen's hydrogen, the red hydrogen, is 3 bonds away from the 2 blue hydrogens. So if the red hydrogen is 3 bonds away from the 2 blue hydrogens, then you should have expected this red hydrogen to be a triplet because it's split by the 2 blue hydrogens, and the 2 blue hydrogens should be a doublet because they're split by the red hydrogen. And it's not. These are singlets. And the memorizable quote that you have to deal with is hydrogens that can make hydrogen bonds, such as alcohols, amines, and carboxylic acids, do not split, and they do not cause splitting. So this hydrogen right here actually will always be a singlet. I said the term always, so clearly there's going to be some exceptions, but we'll avoid those. So in the context of this course, using the examples that I will choose for you, alcohols will always show up as singlets, and they will not cause splitting of the hydrogens on the carbon that the oxygen is connected to. So those hydrogens that are 3 bonds away will also not get split because of the alcohol. Now, if there was some hydrogens over here on the left-hand side, which there currently aren't, then they could definitely cause these blue hydrogens to split. But the alcohol hydrogen will not cause splitting. And the reason for that is because the alcohol hydrogen is actually busy making hydrogen bonds. And in making hydrogen bonds, it physically pulls that hydrogen further away, far enough away that its magnetic field is no longer interacting meaningfully with the magnetic field of the blue hydrogens, so they don't couple. So hydrogen bonding actually decouples hydrogens from each other. That's why these will end up making singlets. Because alcohols wander all over the map, one of the things that chemists will do in the laboratory is they will conduct a typical NMR spectrum, and they have added TMS here to give us the 0 point, and then they didn't quite put it at 0. Shame on them. This peak right here, I believe, is a solvent that is not chloroform. I think it's DMSO. And so this right here is just a solvent peak, but we have the 3 basic peaks that you expect to see, one for the aromatic cluster, and then these 2, the blue peaks right here, and then the red peak right there. So that's your typical spectrum. And they'll conduct this, they'll collect the data, and then what they'll do is they'll change out the solvent. So instead of solvating it in what I think is DMSO, they'll take their sample and solvate it in D2O. Now, deuteriums do not produce peaks in a proton NMR spectrum. They are an isotope of hydrogen protons that do not show up in the same region of a proton NMR spectrum as all the data that we're collecting. And deuterium will actually exchange out because of the network of hydrogen bonds that this red hydrogen is playing with. It's participating in hydrogen bonds with the solvent. This oxygen starts to lose track of which hydrogen it was originally bound to and the other hydrogens in that network. Since those hydrogens were actually deuteriums, what happens is this hydrogen gets kind of wanders off and gets replaced by a deuterium, and this peak goes away. So a lot of times you'll see a note. They'll list out the spectral data. This happens in peer-reviewed publications. Rather than show you the graph, they'll just say we saw a peak at 2.6, a peak at 4.7, and a large cluster at 7.2 to 7.5. And then they'll have a little footnote on there that says the peak at 2.6 exchanged with D2O. And that tells you that that peak at 2.6 is a hydrogen that can make hydrogen bonds. So that's how they know that they had an alcohol. That's how they find the alcohol. A couple of other unfortunate occurrences with proton NMR spectroscopy occur with long-chain alkanes. So notice that there is a group of hydrogens here, a second group here, a third group, a fourth group, and a fifth group. So there are 5 different types of hydrogens in this compound, but you'll only see 1, 2, 3, 4 different peak clusters that are occurring. This peak cluster is a nice, rounded out, well-defined triplet that is the most de-shielded, So it definitely applies to the two hydrogens on this carbon right here. They have the highest shift value because they are directly underneath the chlorine, and they're a triplet because the neighbor over here on the side has two hydrogens. So the two hydrogens here are splitting these hydrogens' peak into a triplet. These two hydrogens right here would be the next most de-shielded peak. And they are being split by two hydrogens on the left-hand side and two more hydrogens on the right-hand side. So that's a pentet, 1, 2, 3, 4, 5. These two hydrogens would also be a pentet. These two hydrogens right here would also be a sextet. Well, at that point, we just call them multiplets. And then these three hydrogens out on the end would be a triplet. Now, I can definitely see those three hydrogens out on the end as a triplet, but what's happening right here, notice the lack of symmetry here, that it looks feathered. And what's going on here is that the peak that has been split into a pentet for these two hydrogens and the peak that has been split into a sextet because of those two hydrogens are overlapping. And so this is the same idea of shadows. Imagine that you put up your hand and you cast a shadow on the wall. That would be the pentet, and then you had a six-fingered hand from the Princess Bride, and you held that up about a foot away from your first hand, but so that it cast a shadow, and those two shadows would overlap, and you'd end up with a mega peak right here. And this is common. When you have long-chain alkanes, what starts to happen is you lose the ability to distinguish peak clusters, and instead of seeing 5 distinct peak clusters, 2 or more of them will just kind of overlap directly on top of each other. And it's a mess, and this is why proton NMR spectroscopy does not always allow you to determine exactly the nature of the compound. C13 NMR would be helpful because you would see 1, 2, 3, 4, 5 distinct carbon peaks. And since carbons always show up as nice, clean singlets, then it would be easier to tell what was going on. There's also this weird thing that alkynes do, and aldehydes do this to some extent, is a carbon-carbon triple bond is a very short bond. And so when you are counting bonds, so from this blue hydrogen to the carbon is one bond. From this carbon across the triple bond is a second bond. And from this sp hybridized black carbon to this sp3 hybridized carbon would be the third bond. And out to those two other blue hydrogens would be your fourth bond. So the blue hydrogens here are 4 bonds away from each other. But they are coupled. And the reason that they are coupled is because the triple bond is so short that it doesn't actually count as a full bond. So they're kind of like 3.5 bonds away from each other, and it allows for something that's referred to as J4 coupling. And this is unique to triple bonds, and aldehydes will do this to some extent. Again, this is an issue of you got to know when to fold them. If you are looking at a terminal alkyne or an aldehyde and the peak splitting doesn't make sense, then there might be a reason for that, and it's because of this complex splitting, or in this case called long-range splitting. And it's obvious once you start to look at these peaks that there are 6 little peaks here, but this lacks the symmetry that we typically see, where it should go small, medium, tall, tall, medium, small. Instead, it's just not that level of symmetry. It's not like every other peak cluster that we see, where again, this is small, medium, tall, tall, medium, small. This is a nice normal peak cluster. This right here is because something weird is going on, and it's the weirdness associated with this hydrogen out here on the end. C13 NMR is probably the easiest to interpret. Of the 4 things that NMR spectroscopy tells you, C13 NMR really only gives you 2 of those things. It is the number of carbons and their approximate shift values. This table right here has more detail than you really need to look at. This comes from your textbook, and what you should appreciate are, if it is part of an alkane, then take all 4 of these and kind of lump them into one idea. Alkanes show up between 0 and 40, alkynes between 65 and 90, alkenes between 100 and 150, aromatic rings between 110 and 175. So there are 1, 2, 3, 4 discrete kind of values that you should memorize. If your carbon is connected to an atom of higher electronegativity, such as an oxygen, a nitrogen, or a halogen, then it will have a higher shift value because of the electronegativity of the atom that it's connected to. Oxygen is the only value that you should actually take the time to memorize. It's about 50 to 70 is a better estimation. Other atoms, such as nitrogen and the halogens, aren't quite as electronegative as oxygen, so they're going to be less than that. Rather than memorize the numerical value, I would just memorize the trend. Oxygen is a numerical value worth knowing, 50 to 70. The other electronegative atoms are going to be less than oxygen. Carbon-nitrogen triple bonds do not show up, do not make a significant appearance in this course. Carbon-oxygen double bonds do show up in this course if they are part of a carboxylic acid or an ester. They're going to barely creep out of the range of aromatic carbons. But if they're an aldehyde or a ketone, then they're generally above 200. So carbonyls are higher than aromatic ring systems. So let's take an example of this and see what we can see. This is a phenol with a methyl group at the meta position. So meta methyl phenol. There's also, it's correct to call this a toluene with a hydroxy group at the meta position. That's a name that I've seen as well, so you can call it meta-hydroxytoluene or 3-hydroxytoluene if for some reason you don't like the word meta. This carbon out here that is part of a methyl group is going to be in the range of 0 to 40. A methyl group can show up below 20. In fact, it's the only thing I've ever seen in a C13 NMR that gets below 20. But if the methyl group is attached to some things that are going to cause the values to be higher, the methyl group will get above 20. So it's kind of a one-way rule. If it's below 20, it's almost definitely a methyl group. If it's above 20, it still could be a methyl group, but you don't know. Then the remaining 1, 2, 3, 4, 5, 6 carbons, all 6 of these carbons would be different, produce 1, 2, 3, 4, 5, 6 different peaks. The peak of the carbon that's directly underneath the oxygen, this is not an alcohol. An alcohol, by definition, has a carbon that is sp3 hybridized, whereas this carbon is sp2 hybridized. This is referred to as an enol. That's where the word phenol comes from. And they behave more like benzene carbons, but their shift values are on the high end of the benzene spectrum. So this peak around 160-ish is definitely going to be this carbon that's underneath the oxygen. It's a benzene carbon, but because of the oxygen, it's going to be a little higher than normal. And then the other 1, 2, 3, 4 carbons that I have not circled have a hydrogen on which to feed for electron density. That causes them to be shielded. So these 4 carbon peaks right here that are closer to TMS, that are shielded, are going to be the 4 with the hydrogens. The one with the carbon will be this one right here. That's definitely not next to an oxygen, but it doesn't have a hydrogen to feed on, so it kind of is in the middle ground. 2 things. One, this is the deuterated chloroform solvent that we typically use in these experiments. There is some coupling that will occur. I think it's between the chlorine and the carbon that actually causes your chloroform solvent peak to be this triplet right here. And you see that show up in a lot of C13 spectra, and I always forget about it because I'm so used to looking past it. Again, much like looking through the window without noticing the glass, you look through the solvent peak without actually seeing it. The last thing is, notice how thick that baseline is. That's what's referred to as the noise. And the noise is due to the fact that C13 NMR experiments are measuring only the carbons in your sample that represent the C13 isotopes. C13 isotopes are definitely less abundant. There's only about 1% of any carbon sample is going to be C13. And what this means is that you have very, very few carbon atoms that are actually producing any signal. And so you have to kind of zoom right in on the baseline to look for any peak that crawls up higher than the noise. And this is still a very nice looking C13 NMR. I have looked at C13 NMR where the peaks in this, the highest peak from the C13 NMR looks more like this little shoulder peak right here. And those are ones where you barely isolate enough compound in the laboratory. You try to run a C13 NMR experiment on it, and the concentration is so low that you barely see the peaks rise above the noise. So this is common for C13 NMR. It's a little messier. It's harder to collect data. That's because the C13 isotope is so infrequent in the universe. Here's another example of a normal C13 NMR. Notice the title says the word normal, which means I'm about to show you something that's not normal, which is actually kind of cool. It allows us to learn a lot more about carbon-13 NMR. So But first, let's just focus on the normal carbon-13 NMR. And I went ahead, or I let the book do it. The book went ahead and gave me this diagram, and it labeled each of these peaks with the type of carbon that it is. So this methyl group out here on the end, notice how it's the only thing in the spectrum that shows up below 20, and it's also the only methyl group anywhere in your compound. So this CH3 group is over here. Then you have 1, 2, 3 different CH2 groups. As they get progressively closer towards the carbonyl, you would expect them to become progressively more de-shielded. So this CH2 right here is probably this one next to the methyl group, and the CH2 group over here is probably the one next to the carbonyl. The carbonyl oxygen, this is a ketone, so it shows up usually above 200. In this case, it's just right below 200. Close enough. And then you have 5 carbons inside of the benzene ring. But there is some symmetry here. So these 2 carbons, the one here and here that are ortho, actually make a single peak. The meta make a single peak, and the para makes a single peak. That's why I only see 1, 2, 3, 4 total peaks in the benzene region, because some of the carbons are NMR equivalent. Okay, so notice here how I have, again, the book has done this for me, so I'm taking credit for that. I have coded all of the CH2 groups in pink, and the carbons that don't have any hydrogens are in blue. And I've divided my carbons up into 3 categories. Carbons with no hydrogens are blue. Carbons with 1 or 3 hydrogens, I did not label. We'll call those the odd numbered hydrogens. And carbons with an even number of hydrogens, of which the only option we ever see is CH2, are labeled in pink. That's what we see in a normal C13 NMR. What they did is they came up with a technique called distortionless enhanced polarization transfer, and mercifully abbreviated as DEPT or DEPT. And in a DEPT C13 NMR, there's actually several different ways of running this. In a DEPT C13 NMR, it inverts the carbons that are bound to an even number of hydrogen. So it produces a very similar spectrum, but notice how now this is the baseline right here, and some of the peaks are going the wrong direction. That is the nature of how a DEPT experiment produces data. And it will specifically invert those carbons that are attached to 2 hydrogens. The carbons with 1 or 3 hydrogens are not affected by this DEPT experiment, and the carbons without any hydrogens at all disappear. This is really quite nice because a DEPT C13 NMR experiment allows you to know exactly how many hydrogens, or approximately how many hydrogens, because CH and CH3s do the same thing, are on each of your carbons. So this is typically how the data is reported. Here is the molecular formula. Here is the normal C13 NMR experiment. It shows you that this produced 5 different peaks, and then in the DEPT experiment, it tells you which peaks were up, which peaks were down, and which peaks disappeared entirely. Using only the DEPT experiment detail and the chemical formula, it actually is pretty simple. It's common for you to be able to come up with a compound with just that information. So knowing that the molecular formula is C5H11Br, the first thing I'm going to do, that I always do, is calculate my index of hydrogen deficiency. My index of hydrogen deficiency is equal to 2 times the number of carbons, which is 5, plus 2, minus any hydrogens that I see, and any halogens that I see. So, and then we divide this by 2, and that's going to give me 0. 2 times 5 plus 2 is 12, minus sum of 11 and 1, which is 12 minus 12. So the index of hydrogen deficiency is 0, which means there are no rings and no pi bonds in this particular compound. That is a lot of useful information. I actually would have known that there's no pi bonds, because a pi bond between 2 carbons would be an alkene, and that alkene would have showed up between about 100 and 150 in my C13 NMR. So knowing that there's no pi bonds or rings in the system, I'm going to now start building this out. I have a peak at 51.55. That is really high for an alkane, and the best explanation for how a carbon could have such a high value is because that is the carbon that is directly connected to the bromine. So this carbon that shows up here at 51.55 is the carbon that's connected to the bromine. And that carbon in the depth experiment is up. Now, up means that it has either one hydrogen or three hydrogens. And it's not three. If it were three, then the molecule would be methyl bromide and there would be no way to attach more bonds. I've closed off both ends. Bromine makes one bond, carbon makes four bonds, they're done. So I can't continue to build a molecule off that. So instead, this is a carbon that is bound to four things, and one of those things is hydrogen. Now, I know that it's sp3 because sp2 carbons are those that participate in pi bonds. My index of hydrogen deficiency is telling me there's no pi bonds, and the shift values say that all of these are just simple alkanes. So if this carbon is sp3 and bound to four things, based on the depth, only one of those four things is a hydrogen, and the other two have to be carbons. I built this much of the structure just based on an index of hydrogen deficiency of 0 and this one peak at 51.55 with the depth telling me that it was either CH or CH3. That's it. So I have already accounted for 3 of my carbons. Now I need to account for 2 more. If I try to attach both of those carbons off of the end, so I'll put one carbon here and one carbon like this to make this molecule, then unfortunately what I just did was generate a line of symmetry. These two methyl groups would actually be exactly identical, and so they would produce only a single peak in my C13 NMR spectrum. This molecule that I've proposed, 3-bromopentane, would only generate 3 C13 NMR peaks, so it's wrong. So I'm going to go back and try that again. So that did not work. Consider what are other options that are available to me. So if I couldn't just put methyl groups on either end, then let's just put a methyl group on one end. And I still have one more carbon to add. I can't put it here because that would produce a symmetrical compound. I could put it right here, but that would also produce some symmetry right here. Those two methyl groups would be the same. So the only way to generate 5 unique carbon peaks is to attach those 2 remaining carbons off the same end right there. Now let's check to see what the, let's clean this up. There we go. I like that structure more. Let's see what the depth experiment would tell us. This carbon we would expect to be the most de-shielded because it's directly underneath the bromine. It has a value of 51.55. The depth experiment tells me that it's up, which means that it's a CH group or a CH3, but unlikely to be a CH3. The next highest shift value would be one of the carbons that's adjacent to the carbon carrying the burden of the bromine. That's this one at 43.22, and that would be down. That's the CH2 group. That makes sense. Then we have another down peak at 26.46, and then a methyl group that is above 20, which means that that methyl group is adjacent to some weirdness, which is what the bromine is, and a methyl group that's below 20, which is a more standard methyl group. So I'm comfortable with this as a possible answer given this data. Let's go ahead and generate a C13 NMR structure to see if I made a mistake. And so we came up with these values right here. Let's go ahead and copy and paste those back to compare them with the values that were listed for me. That's going to be a problem. So we had 50.7 and this one had 51.55, 43.7, 43.22. These approximately match up. That's interesting. That methyl group they're showing is 26.8 and I had it at 21. That might be a difference between real data and NMR data that ChemDraw predicts. I'm still comfortable with this as my answer right here. The depth experiment matches up quite nicely. Okay, let's take a look at this one, but not using ChemDraw. So C4H8O, index of hydrogen deficiency, is equal to, well, the number of carbons times 2 plus 2 is 4 times 2 plus 2 is 10. There are 8 hydrogens. Oxygen has no effect, so 10 minus 8 divided by 2 tells me that my index of hydrogen deficiency is 1. This C13 NMR peak right here tells me that I have either an aldehyde or a ketone. That aldehyde or ketone, let's go ahead and go back to ChemDraw. Aldehydes and ketones are going to produce different depth readings. The definition of a ketone is that it is a carbon that is connected to two other carbons. That's how we define ketones. So we're going to have a carbon over here if it's a ketone, whereas if it's an aldehyde, then one of these will be a hydrogen. So if you see a peak at 200, then, and it's going to be either an aldehyde or a ketone, then the depth experiment will tell you which of the two it is. If it has no hydrogens, then by definition it can't be an aldehyde. Therefore, my molecule has a ketone. And so it's got to be a carbon like this. So based on that one peak at 208 point something, knowing that the depth told me that there were no hydrogens, I already built the vast majority of my molecule. And I also accounted for the pi bond. While oxygen does not affect my index of hydrogen deficiency calculations, a pi bond between a carbon and an oxygen is represented as a value of 1 on my IHD calculation. So I've already accounted for the pi bond. All I have left to do is put one more carbon. Since I can't make it a ring, then the only option I have is to put that carbon out here on one of the two ends, and it would be the same either way. So this is my proposed molecule. Let's see how that molecule matches up against the data. So I'll just put this molecule down here as a point of reference. This carbon right here is the peak at 208.7. It has no hydrogens, which matches up with the depth. Of the two carbons that are adjacent to the carbonyl group, you typically expect the methylene to have a higher shift value than the methyl. This CH2 group, which would be down, is 37.6. The methyl group is 30.1. That is really high for a methyl group, but it's adjacent to a carbonyl, so I'm okay with that. And then we have this more standard methyl that's up and out at 9.2, which is the hallmark of a boring methyl group. So this is probably the correct answer for this compound. Really the only answer that I could think of. So now you're ready. You have learned everything there is to know about spectroscopy. I'm laughing because you probably haven't learned everything that I've said. I've said everything that I'm going to say about spectroscopy. From here until the next exam, what I'm going to do is give you practice problems and then provide an explanation for those practice problems. So there's not really any new information. When you look at a question like this, you have to identify first, what types of spectroscopy am I looking at? Well, ppm is the axis label on the x-axis for NMR spectroscopy. If it goes from 0 to 180, that's definitely C13 NMR spectroscopy. If it goes from 0 to about 12, that's your proton NMR spectroscopy. So C13 NMR, proton NMR, and then here I didn't give you either of the axes, which is an insult to the very nature of science itself, but I did tell you that the molecular ion peak is this one right here at 59. So that's mass spec right there. And the only peaks that I've identified for you are the peak at 59 and the peak at 44. When you don't know anything at all, start with a mass spec and ask yourself, what evidence do I have for the non-hydrogen carbon atoms being present in my spectrum? Honk X. Mass spec tells you whether or not there's a nitrogen or whether or not there's a halogen. It doesn't tell you, but it hints. If there's a halogen, your molecular ion peak here at 59 will show a prominent M+2 peak. If it's about a third as tall, which would be about this tall, it's a chlorine. If it's about the same height, which would be about this tall, it's a bromine. Neither. So there's no good evidence for chlorine or bromine. If the mass of the compound is odd, that would suggest an odd number of nitrogens. So this compound most likely has a nitrogen. After looking at the molecular ion peak and figuring out if there's nitrogens or halogens, anything else you can pull out of the mass spec is bonus. And the only thing worth noting here is the numerical gap from 59 to 44 suggests that somewhere in your molecule you have a methyl group. And that's not really that helpful, because looking up at your C13 NMR, you see a peak just above 20 that is up in the depth experiment. That's going to be probably a methyl group. Up means that the carbon is attached to an odd number of hydrogens. CH, methine carbons, tend to be closer to 40. Methyl groups are down here around 20. So the fact that there is a 15 gap right there is actually a bit redundant, because I could have figured that there's a methyl group right there in my C13 NMR. There is only one other peak in my C13 NMR, and it shows up above 160, above 170. That's generally where we see very odd benzene carbons or a carbonyl carbon that is attached to a heteroatom. Okay? So from this peak at about 175, that is going to be a carbonyl group, and the carbonyl group is going to be attached to either an oxygen or a halogen or a nitrogen, and it's probably a nitrogen. Okay? So let me then, from those compounds, actually at this point it'd be great for you to pause the video and try to come up with the structure yourself, and then come back and I'll finish walking you through the rest of the explanation. Okay, let's see if you're ready to come up with the right answer. So I probably have a carbonyl group right there. I have a nitrogen right there, and I have a methyl group. A carbonyl weighs 28, a nitrogen weighs 14, and a methyl group weighs 15. 14 and 15, so sorry, the nitrogen weighs 14, methyl group weighs 15. That's a mass of 29. A carbonyl group weighs 28. 29 and 28 is 57. I only have 2 other units of mass. So that means in addition to the carbonyl and the nitrogen and the methyl group, I have 2 hydrogens. There's the structure of the compound right there. This is kind of a nice little spiral moment right there. So there's my carbonyl group, there's my methyl group, there's my nitrogen, and there's my last 2 hydrogens. This methyl group right here is what accounts for this singlet of 3 hydrogens. Those 3 hydrogens are 3 bonds away from everybody. And the fact that this is a singlet with 2 hydrogens that exchanges with the D2O there's a lot of information packed in this statement. Anything that exchanges with D2O is going to make hydrogen bonds. So it's going to be a singlet. The fact that you have a singlet of 2 hydrogens is generally not going to show up with an alcohol, because alcohols only have 1 hydrogen. So amines, or in this case amides, when you count in the carbonyl group, this nitrogen with 2 hydrogens is what's making those peaks right there. So when this molecule falls apart, what happens is it forms the cation radical on this nitrogen and then clips off this methyl group. That's this gap that we get right there. This CH3 group is the up peak, and then this carbon-oxygen peak disappears in the depth experiment because it doesn't have any hydrogens associated with it. So hopefully you were able to get that one, and hopefully you took the time to practice it.